All right, everyone. My name is Zeb Kurtzman, and I am presenting uh, green chemistry focused on something called micellar catalysis. So a little preface. I am an organic chemist by passion, mainly, not yet practicing, but we'll get there. Um, and one of the things that I'm really interested in is I'm obviously interested as an organic chemist in making molecules, making complex molecules. I like, focus on making, finding routes to natural products, routes to medicinally relevant compounds. And along the lines of kind of natural product synthesis, the thing that kind of inspired me the most is the ability of organisms and plants to create these molecules, that inspire so much of our medicines and that kind of thing. And the way that biology creates molecules is really interesting to me. Instead of using organic solvents and exotic reagents, biology creates all of its processes, through evolution. They do it in water, which is incredible, and they create very specific products. They create these molecules with all these stereo centers, super complex, and a lot of medicines don't work without this specific kind of synthesis. So this topic is a green chemistry topic. And kind of one of the things that got me thinking about it is, during our 501 seminars, at least for first year PhD students, we had a presentation by Dr. Ian Gould, the general organic chemistry, one of the general organic chemistry lectures at ASU. And he kind of takes an approach to doing synthesis in water, but not by modeling it after biology, but by modeling it after geochemistry. And his lab kind of focuses on doing reactions at super high temperatures and super high pressures on these hydrocarbon molecules to create useful molecules out of them. But I kind of am looking at a different approach right now, and that's more of a biomimetic approach. Not quite talking about biocatalysis, although that is going to be part of this topic, but more focusing generally on how nature does chemistry. So just to get into it, what is micellar catalysis? Well, the question is, what is a micelle? And so in cells, the way our cell membranes are formed just with these phospholipid fatty acids, where you have the hydrophilic head, the phosphate part, and the lipophilic hydrocarbon tail. And at super high levels, what this will do is it'll form a bilayer where you have the hydrophilic head facing towards the water on both ends, and the hydrophobic core facing on the inside, those tails facing on the inside. But at lower concentrations, what a lot of surfactants do, and surfactants kind of, like soap, detergents involve surfactants, is they'll form these supramolecular assemblies called micelles, which essentially are more just little spheres of surfactants, where you have a hydrophilic surface and then just the hydrophobic interior. You don't have this bilayer, but you have a hydrophilic surface of water soluble portions of the molecule facing outward, and this hydrophobic tail interior facing inwards. So these in water, these surfactant molecules will aggregate to form these micelles, and they have a hydrophobic core and a hydrophilic surface. And the point of micelles in this talk is essentially that these micelles will help to solubilize water insoluble substrates. And the main route to catalysis, or at least the first layer of this route to catalysis, is this increases their concentration within the micelle, and thus kind of pushes equilibrium towards the products. And you can't do this in organic solvents as a bulk medium. because if you concentrate your products too much in organic solvents, even they won't dissolve. So you don't get this high concentration within a specific area within a bulk organic solvent, but by using micelles, surfactants at a certain concentration in water, you can do this, and the concentration of the surfactant doesn't even have to be particularly high. You'll see in the examples I use, it's about 2% per 2% of weight of the total bulk reaction medium, where 98% of the weight is water, and then 2% of that weight is in surfactants, and that's really all you need to form these micelles. And by modifying these surfactants, you can create micelles of various size. And then another very interesting thing is you can even attach catalysts to these micelles to further further go along the process. But why do this? Well, generally, again, chemists don't really think about, we think about solvents for running reactions, but we don't really think about the overall cost of using these solvents. So organic solvents are generally environmentally hazardous and toxic. Benzene, famous benzene, carcinogenic. A lot of the ethers are volatile and make you dizzy, can make you pass out. They're not good for your body. Same thing with chlorinated solvents. Carbon tet, very carcinogenic. Dichloromethane is also, and chloroform are not very good for you, and they don't generally have, they have very they're very volatile, and they're pretty toxic. And they also organic solvents account for the majority of waste, and therefore environmental, the environmental externalities of organic synthesis. And I couldn't find the exact source, so I didn't want to say it here, but just reading about this topic, kind of going into green chemistry, they can account for like 80 to 85% of the environmental waste, if you're just talking about organic solvents, of a lot of pharmaceutical processes. So, instead of using organic solvents, why don't we use water? Well, water is cheap, it's environmentally benign, it's non-toxic, and of course, with all those attributes, it's too good to be true. Because unfortunately, many organic substrates, are not water soluble by definition. They have little to no solubility in an aqueous environment, because they are hydrophobic, generally hydrophobic molecules. And we already know that, because most organic solvents, by definition, organic solvents are water insoluble. They are mostly only soluble in specific organic solvents. But the solution here, or one of the solutions here, is micelles, which require, again, relatively low surfactant concentration. And the hydrophilic interior of these help to solubilize these water insoluble products. They also, when you attach catalysts to them, they require relatively low concentrations, low temperatures. So a lot of these reactions in surfactants can be run at low temperatures, and they also offer high recyclability. So in flask recyclability, and even just recycling the surfactants and the catalyst. You can, for a lot of these reactions, you can run them multiple times in the same reaction vessel after extraction. So this is kind of what I was getting to, designer surfactants. So, these are kind of the three approaches when when you're looking at this type of chemistry. You have your classical approach that everyone knows. You have your substrates and organic solvent, go to the products. But that's, again, you're using a lot of organic solvent, generates a high amount of waste, and it's not good for the environment. And then we have this type 1 micellar catalysis, which I was originally talking about. And what happens is your substrates aggregate at very high concentrations within the micelle. And we all know the Chatelier's principle: high concentration reactants will always push the equilibrium towards the products. So we get our product because we aggregate them in this small, this relatively small amount of volume within the micelle. But then this next thing is really what made me really interested in this, and this is kind of designer surfactants. So where you actually attach catalytically active groups and catalysts themselves to the surfactant molecules that lie within the hydrophobic interior, and not only do they gather up the substrates within a high concentration, but they also help to catalyze a reaction like catalysts do. So some of the examples I'll be going over, they include metal organometallic chemistry, organometallic catalysts, and organocatalysts. And these design surfactants help to improve catalyst recycling and reuse. So all of the examples I'm going to be going over come from the work of Dr. Bruce H. Lipshutz from University of California, Santa Barbara. And he has integrated micellar catalysis using water as the primary solvent, but that's a little bit of a misnomer because, again, the solvent is actually the hydrophobic interior of the micelle, and the water is just the bulk reaction medium that allows for this dynamic process to take place. So these micelles aren't static things. They actually, they're in equilibrium. They'll break apart, reform, combine, and by modifying the surfactant, you can also create micelles of different diameters. So you can tailor your surfactant to your specific chemical process. And the main examples I'm going to be going over use this PQS surfactant. So this is derived from coenzyme QA, ubiquinol. So this is kind of the ubiquinol core. They attach this polyethylene glycol head to it. This is the water soluble end of the surfactant. And then you have this lipophilic interior from this long hydrocarbon. But then interestingly, also you have this aromatic phenol here that this acts as a catalytic handle. So this is where you can attach through basic esterification chemistry, just attach your catalytically active moiety. And so some examples of the types of reactions I'll be going over, there's some biocatalytic reactions, some asymmetric organocatalysis, and organometallic catalysis. And again, most of these are based off of this PQS designer surfactant. So the first example I'll be going over is, this ring closing metathesis. In the first lecture talk I actually ever had to give, literature review that I ever had to do, it was a total synthesis that involved this ring closing metathesis, and I was not familiar with organometallics at all. So this one took me a while to even figure out that ring closing metathesis was a type of reaction. Kind of embarrassing, but whatever. So the way this reaction works is you have this metal carbene, right? And you do a 2+2. So anyone who's in Trovich's organometallics class will know what I'm talking about. Does a 2+2 addition where it forms this metallocyclobutane intermediate. It eliminates, again, in a 2+2 fashion to eliminate ethylene. And then you have your metal carbene attached to your diene substrate. Does another 2+2 addition with the other alkene, and then another 2+2 elimination to eject your newly formed alkene ring. So it's a cool reaction. I actually enjoy this one a lot. And so what they did in this 2009 paper or Organic Letters was they took PQS. They did an esterification on this molecule right here as a handle, and it contains this alkene here. So they do the esterification, and then they take their Grubbs catalyst, right? They do an olefin metathesis to attach their Grubbs catalyst and also coordinate this oxygen right here to help hold it in place. And this is what the final, this catalyst is, the catalyst 2 is referring to this final molecule where you have your PQS hydrophilic portion, helps solubilize water, lipophilic side chain, forms the lipophilic interior, and then your carbene metal catalyst that performs the alkene metathesis. And this lies in the hydrophobic interior of the molecule. So that's how they make the catalyst. And you'll notice it does involve the original synthesis. So this does involve, organic solvents. Unfortunately, it's hard to get away from them completely, but from what I was reading, I didn't really include it, but what I was reading is they actually did find better ways towards this surfactant. But you're not going to be able to you're not going to be able to avoid organic solvents completely. You still need them to extract your final product, but all in all, you're using way less of this organic solvent than you would in a normal process where you run it as your solvent, your main solvent. So they calculated their E factors, and I couldn't find the exact papers, but I was kind of watching an ACS talk. And according to them, their environmental factors, so which that's the kilograms of kilograms of chemicals, not including water, that you use over your kilograms of product, and that gives you your E factor. So theirs with these end up being an entire order of magnitude less than a normal process. And they're able to get these fantastic yields with all these different substrates in water at room temperature with only 2% of their surfactant catalyst. But not only that, they are able to recycle this catalyst in flasks. So they do the reaction with the surfactant catalyst in their substrate. They'll extract their products with a small amount of ethyl acetate. Again, much less organic solvent than you normally use, and you could recycle your organic solvent over and over. So again, really reduces the waste, and they can do this up to 10 times in flask versus just just the Grubbs catalyst with surfactant, or just the Grubbs catalyst alone in water. Like they're able to really help recycle this this precious metal catalyst, and they're able to do it at room temperature. So again, less organic or less environmental waste through even reduced electricity costs, reduced time getting the reaction up to temperature. And again, the only organic solvent used is ethyl acetate for product extraction, and I don't believe it was that much. So and then even more impressively, they were able to run this reaction in just regular old seawater. So, they went to, University of California. They're able to go to the ocean more than us Arizonans are. So go over to the ocean, they just grabbed some seawater. They didn't put it in our atmosphere. They didn't degas it. And they were able to run this reaction with a 79% yield at room temperature and just regular old seawater. And again, this type of approach allows for continuous batch processing where water and catalyst do not leave the reaction mixture. And then another thing that I was able to find, to kind of connect it to this class was a PQS-enabled iridium photoredox catalysis in water. So they were able to, again, take this coenzyme Q10, they hydrogenate it to essentially aromatize the ring and give you your hydroxyl groups. This allows them to attach esterified to the polyethylene glycol succinic acid handle that gives it its hydrophilic character. They take their iridium catalyst, right? So, and then they brominate it. And then this is the handle for the iridium catalyst. They make it the pinacol ester, and then they esterify it to the PQS, and then they just do a Suzuki coupling to ultimately attach the catalyst. And then these form micelles between 30 nanometers and 60 nanometers, that's a typo, in diameter. And they tested it. They got an oxidation peak of plus 75 volts versus a saturated cal mole electrode. So, and so this was the reaction they run. They have this what is that? So they have their substrate right here. and they do this photo redox catalysis to couple these together using blue LED light at room temperature in water. And they're able to form these products in, upwards of, lowest end being 50% yields, but mostly in the 90% yield range. So they compared this to the non-PQS linked iridium catalyst in water and yielded this 11A product, only 23% yield. They found that this PQS linked iridium complex could be recycled in flasks for 4 runs with yields between 70 and 88% before another, half molar percent catalyst had to be added. And it performed better with more recyclability than the free iridium catalyst in a surfactant solution. So I believe this first example is just running it in water with no surfactant. And then running it in water with surfactant, but not attached to the catalyst. So they were able to do, both both the reaction in water with free surfactant, and then they compared that to the surfactant attached catalyst, and it was essentially able to run a lot better and was also able to be recycled in flask more than the free catalyst with surfactant. So that was cool. Next example involves asymmetric organocatalysis. So asymmetric organocatalysis was the subject of this most recent Nobel Prize in chemistry. And so essentially what they did is they used the same PQS base and attached it to a proline catalyst, which is capable of catalyzing asymmetric aldol reactions. So they tested this against, there's a PQS proline yields of 93% with, the specific substrate scope, anti-syn ratios 92:8, and enantiomeric excesses of 96%, versus this C4 ester here was only able to get, they couldn't really get any measurable yields, less than 5%, and then just free proline, again, they weren't able to get any yields. This is in water, so in water at room temperature. And it also offered, again, high in-flask catalyst recycling. So, they did this same reaction with their surfactant catalyst, and they didn't see very much loss after 4 in-flask runs. So again, they do the reaction, they extract with a small amount of organic solvent, and then they just add their substrates again. And, you'll see here 4 runs, upwards of 90% yields, comparable efficacy, and they keep their enantiomeric excesses, right? Okay, so that's our designer surfactant portion, but now I'll just talk about what just surfactant is capable of doing. So this relates to biocatalysis, and in this experiment they were able to successfully pair metal catalyzed coupling reactions with biocatalysis in a 1-pot 2-step process. So in this one, they're not using the PQS surfactant, they're using this TPGS surfactant, which uses vitamin E as a lipophilic core, and this PEG again is the hydrophilic part of the molecule. Or no, I don't think this is PEG, this is something else, but a similar hydrophilic part. And the cool thing about this is I'm not really sure how non-toxic the PQS detergent is, but this is very non-toxic. These are benign by design. These are not environmentally harmful to dispose of. Vitamin E is a natural molecule, and is very biologically benign. And so what they do is they first do their metal catalyzed coupling. So in this example, you have this Sonaga-Shira coupling. So they couple this aromatic with this alkyne here, right? Using one of these 2 processes. So these processes involve palladium catalyst, copper iodide, this triethylamine base, and then they use 2% weight of TPGS in water at room temperature overnight, and that gives this intermediate here, and then they add their alcohol dehydrogenase, which is actually working reverse of this is working the reverse process more than anything. It's not, you're not going from an alcohol to a ketone, but you're going from a ketone to a an antioselective alcohol. So you only get one of these enantiomers. So in pure water with this product, they're able to get 99% yields, 99.9% enantiomeric excesses. We're slightly down in yield with this substrate to 79%, but still, almost 100% enantiomeric excesses. So this is a cool way to pair metal coupling reactions to biocatalytic reactions. And kind of what they found here that's really cool, and this is kind of the biomimetic approach at work here, is that the micelles essentially act as reservoirs for the hydrophobic substrates and products. So, with regular enzymes, if you overload the concentration of substrates too high, you'll basically overwhelm the enzyme and it won't be able to perform its function, essentially blocking out the active site. But what this does is essentially, acts as a reservoir for the substrates and products, so it takes them out of the equilibrium. And the reason this is also so cool is that one of the big challenges with biocatalysts is kind of a similar one to just the problem of running organic reactions in water, except biocatalysts almost have to be run in a water solution, because that's how enzymes work in biology. Is their folding depends on being in water, because you have your hydrophilic part of your hydrophilic side chains that'll phase out and create this hydrophilic interior at the active site. And if you can't really run biocatalytic reactions in anything but water, because their native functions are determined by folding in water. So this kind of helps bridge the gap, not only between organometallic reactions and biocatalysts in this one pot two-step process, but also just helps improve biocatalysis in general, because now you can actually run you can run a lot more reactions with biocatalysts, because you're able to solubilize your substrates in the water. And kind of another thing is that they also found that just with the biocatalyst, the concentration of micelles and actually the hydrophobicity of the substrates, as those increased, the efficacy of the enzyme actually also increased. So this kind of helps bridge that gap. In conclusion, micellar catalysis can play an important role in making synthesis green. And the primary way it does that is it helps eliminate the reliance on environmentally harmful organic solvents. Another kind of a benefit of this is, because a lot of these reactions are able to run without excessive heating, mostly room temperature, ambient temperatures, you get a lot less side products and a lot less side reactions, which are usually driven by an excess of heat. And they can also help bridge the gap between biocatalysis and more traditional methods. And then another thing I didn't really list here is that attaching catalysts to, especially precious metal catalysts, to these surfactants allow them to be recycled and isolated a lot easier than just running it in a bulk reaction mix of organic solvents. So it kind of helps attack this problem of how do we make synthesis green and environmentally friendly from a few different angles. And the really cool part about this is that it's a very biomimetic approach. It really helps take its inspiration from nature in much the same way biocatalysis does, and could also help improve the efforts of biocatalysis in getting us towards more precise methods of synthesis and ultimately more environmentally friendly ways of synthesis. So yep, thank you.